this. But next up, we have Josephine Baggen, who's going to be talking to us about mass compact galaxies in the early universe.
Oh, still have a mic. I'm so sorry. I'll ask the first question. Is this better? No? Better now? Right, okay. So I'm working in a group of Peter van Dokken, and I'm going to be talking about the information of compactness of three galaxies that we found with detected Balmer breaks at redshift 7 and 8. So introduce this talk, I'm going to be starting with where it all also started for me. In 2022, when I became a first-year student, it was also the first data release of JWST, and this paper came out about 13 massive galaxy candidates. We've seen this already a few times now today. And these were selected based on the double break, so by requiring both the Lyman break and the double break in their spectral energy distribution. And this is very different from selecting only on the Lyman break, because it typically selects also an old stellar population of roughly 100 to 200 megayears old. And the stellar masses derived from these SED kits were really high, 10 to 10 to 10 to the 11 solar mass, at a photometric redshift of 7 to 10. So this is very remarkable, right? You only have a few hundred megayears after the Big Bang to form these systems. How can you require such a large stellar mass? And in fact, a few weeks later, this paper came out by Boyle and Fulton, saying that you really need high efficiency, so converting all the baryons in your halo into stars to get these stellar masses. Otherwise, your intention would land up too low. In my first paper, we measured the sizes of these galaxies, and we found that they are very compact. But most of the sample was actually dissolved, and we found the size to be between 80 and 300 parsecs, with a mean of only 150 parsecs. And using these sizes and the stellar masses from the SED fit, we measured the stellar density profiles, compared them to twice as galaxies at later times. And we actually found that the densities in the inner 100 parsecs is very similar, leading to the idea that what if we just form these cores at redshift 8 already so early, after which they grow in a very simple inside-out way. But of course, people came with other ideas. What if the stellar masses are wrong? Maybe you just need to change IMF, emission lines, but of course also AGN contamination is very likely. But what if we actually have the stellar masses? People came with solutions to this. Maybe you have the speed-free burst regime, where you create these large efficiencies and large stellar masses. But as David Alva just pointed out, there were also a lot of exotic scenarios. Maybe the universe is sizable. But the logical thing to do is then to get follow-up spectroscopy for the sources, and this was obtained in March by the team called Rubies. And three galaxies were found with pronounced Balmer breaks at redshift 6 and 7 and 8, out of which 2 were in Labe. And this actually shows that we were actually looking at the old stellar population. However, very contrasting to the stellar feature in the spectrum, these galaxies also have broad Balmer lines, with sigma is larger than 1000 kilometers per second, which indicates probably that we're looking at a broad line region of the AGN. So playing with different contributions to the spectra, you can play with AGN for the stellar contribution, which leads to very uncertain stellar masses, which I will show in this plot right here. So the top one is a case where you only fit the spectrum with the stellar component, leading to, as you might expect, very large stellar masses of 10 to the 11. The bottom one, you really lower the amount of stellar contribution to the red flux. It really boosts it up by the AGN, and then you get 10 to the 9 solar masses of stellar mass. And then the middle case is something in between, a little bit of both, getting 3 to 10 solar mass. So very uncomfortable, right? We finally have the spectra, but we still have no clue what the stellar masses are within a factor of 100. However, we do know that we've detected this Balmer break. So we do know that around that wavelength, we can expect that the light that we see in the images comes from the stars. So actually the sizes and the images and the morphology really reflects the stellar distribution. So now with the updated redshifts, we measure the sizes and we discuss the implications on density. And that's the paper that I'm working on currently, and that will be the topic of today. So the data that we use comes from CLEARS. We typically find that the galaxies are resolved in the bluer bands, unresolved in the redder bands. So we chose to use the reddest band possible with the highest resolution, but going as close as possible towards the Balmer break. We use GelFit to fit a Searcy profile to these images. And what it does is it creates models, it involves it with the CSF, and then compares it to the image in a chi-squared way. We really, this time, we really try to understand the uncertainties on the sizes that we measured by forward modeling different models, different CSFs, projecting it into different regions of the sky, and we found that the error bars are huge. But one thing that we're going to talk about is that we can confirm that they are ground compact. So, how big are they? They are roughly 100 parsecs in effective radius. So placing this in context, the size will be called the luminosity relation. They are about 100 times smaller than spiral galaxies at fixed magnitude, but also 10 times smaller than Lyman break selected galaxies at the same redshift. And this is actually consistent with many observations recently with JWST. Many groups are finding that massive bright galaxies tend to be very compact. I was interested in whether hydrodynamical simulations actually produce this as well, and it's a bit of a mix. So the FLARE simulation finds that bulge formation can be very efficient, with radii down to 100 parsecs, while the TSIN does not find any of these sizes. So very interesting, we can maybe learn from this. And also a very recent paper 2 weeks ago by Bolchin that you actually expect this compactness based off the dark matter profiles at high rates. Alright, so the implications of these sizes, given the range of stellar masses that we have, what are the inferred densities? So I'm calculating the surface density and compare this to different stellar systems. So here you see a plot of different stellar systems in the universe. So star clusters, ultra-compact dwarfs, and globular clusters are shown in green. Elliptical galaxies in gray, and compact elliptical galaxies in redshift 2 in yellow. Then I'm also showing 3 quiescent galaxies in redshift 4 and 5 with stellar masses of roughly 10 to 11 and are also very compact, roughly 200 parsecs in size. And then the horizontal line is an empirical limit introduced first by Hopkins in 2010 and extended by Grudich in 2019. And then I'm adding the points for our 3 different stellar mass cases. So for the low mass case, medium mass case, and the high mass case. And as you can see, for the high mass case, we're really exceeding surface densities of any stellar system that we see in the universe. We also see this popping up in the stellar mass profiles. So we do the same thing as we did in the first paper. We derived the stellar mass profiles following, which was firstly done in the Zenz in 2009. And we compare this then to central regions of massive quiescent galaxies at later times. So I'm showing the curves for redshift 4, 5, the red nuggets at redshift 2, and redshift 0 ellipticals. And we again find that for the highest stellar mass case, we're really exceeding the inner density in the cores compared to plausible lower redshift settings. But what I'm very interested in is the velocity dispersion for these systems. So what if these systems are in virial equilibrium, and you can expect that you can relate the velocity dispersion to the dynamical mass of the system and the radius. So when the mass is really high and the radius is very small, you might expect that the velocity has to be high in order to be in equilibrium. And what you can do is you can relate the dynamical mass to the stellar mass. You can relate the size of the gas compared to the size of the star, the inclination of the disk. A lot of uncertainties, but you can make a relation for what you predict for the velocity distribution of the gas based off of the stellar mass that you measure in the effective radius. And everything that you don't know, you just put in the constant c. You can play with the constant c, but typically what they assume to be the constant c is 5.906. So an interesting idea then is to measure these 3D systems and compare them to the broad lines that we measured in the spectrum. And that's what I'm going to be showing here. So on the x-axis is the predicted velocity dispersion, on the y-axis the observed velocity dispersion of the h-beta line. And as you can see for the high stellar mass case, they both are in the regime of 1,000, 1,200 kilometers per second. So this actually led us to the idea that what if you just can explain the broad lines not by a broad line region, but just by the fact that these systems are very compact and massive. But it's a wild idea, right? So putting 10 to 11 solar mass in a size of only 100 parsecs, and these systems then are rotating at 1,000 kilometers per second. But to conclude this, we have observed 3 galaxies with Balmer breaks at redshift 7 and 8. And what we find is that understanding the activity is really difficult. You can really play with the AGN contribution versus the stellar contribution. What we do find is that they are very compact, roughly 100 parsecs. A large stellar mass case combined with these sizes lead to extreme densities that we do not observe in the universe in any other system, and extreme velocities, which might be able to explain the broad lines. And actually this might become important for the little red dots as well for others, where they also find broad lines of roughly 1,000 kilometers per second. What I'm very interested in is, are these systems even stable? Might they undergo collapse? Forming black holes, I don't know. Also, what would their velocity of evolution be? We do know that if such systems exist, the density has to lower in order to be consistent with massive galaxies at later times. But we also caution that the HN scenario is likely, perhaps more plausible, but it also has complications. Because, as was shown already before today, they don't really pop up in X-ray. Also, the SEDs using ALMA and MIRI detection favor stellar contribution. They also have no radio detections, and as was explained this morning by Harry Kenny, they also don't show any variability. Maybe we need longer time scales, but I want to end this to say that maybe the nature of these lasers is starting to become even more of a mystery. But for now, I'll just pick your favorite, and you can answer any questions.
Let's go with Mark.
Could you go back to your plot of the densities, the volume densities rather than the surface densities? Yeah, so I mean, I guess you're saying that these are very high, and by galaxy standards, they absolutely are. I just wanted to point out that, I mean, by the standards of star clusters, these aren't actually that high, right? If you put this in stars per cubic parsec, it looks like you're topping out at around 1,000. And I mean, again, that is huge by galaxy standards, but that's nowhere near the density you'd get, say, in the center of a globular cluster.
Right. That's
so, yeah. So I just, we have plenty of stellar systems that are denser than that, just not so big.
Right. But yeah, that's correct. We just compared to what we think are the densest systems in terms of galaxies, which are the quiet ones. But yeah, star clusters can be denser.
Can the next speaker make their way up? And there's another question back here.
This is really interesting. I just want to point out there are some galaxies at low redshift that do have similar ridiculous stellar mass densities. These are starburst galaxies, like major merger starburst galaxies that are driving these extreme outflows. I can show you, there's a paper by Alex Diamond-Stanek in 2021 that has those numbers for the central. They're rare, but they're basically ellipticals in formation, so it sort of fits this general picture.
Okay, thanks.
Yeah, for the, if you go back to the dynamical sort of estimates of the broad lines, have you thought about the O3 here and why the O3 is not broad?
Right. So we looked at O3. It's actually the same argument as why O3 is not broad for BAGNs, because you think it's coming from a narrow dimension. But also in this system, the densities are too high to form O3. So we again say that O3 must come from further out. But the resolution in the 2D prism, we cannot resolve that. So it would be a really interesting idea to see where O3, the narrow O3 line comes from. Right. But we're talking about 10 to 6 and so, well, exactly. Yeah. Well.
I was just wondering, in thinking about dense stellar systems, in the largest ellipticals, they probably had their centers excavated by merging black holes. And before that happened, they might have been denser. So I just wondered if you'd taken that thought into account.
I actually had another slide, but for the sake of time I didn't add it. But there was actually also a paper this morning explaining how supermassive black holes can lower the densities in red metals. Yeah, the black hole scouring, many things can for AGN feedback.
Thank Josephine again.